Welcome everyone to section 1.3. We're going to talk about slope fields today. And you might be expecting some cool explanation for why slope fields have something to do with my cat Theodore, but there is none. This is my cat Theodore. Anyway, so let's talk about what is a slope field. And the way that we're going to do that is we are going to brightness alert. We're going to go back to this mixing problem from the previous section. So remember, in this problem, we had this tank of 100 gallons, and we were putting in two different solutions from two different pipes, and we were pumping out a mixed solution. And we were curious about, okay, what does the sugar level look like in this vat over a long period of time? And what we did is we found out that it followed this situation. We have a vertical translation. This is the eventual steady state. And we have this exponential portion. This might be exponential growth. This might be exponential decay. It really depends on where we start, which makes sense, right? If we don't start with any sugar and we're pumping in sugar, we will eventually approach that equilibrium level that we're pumping in. And if we have a ton of sugar in the tank and we're pumping in something with a lower concentration, we will eventually get down to the concentration that we've pumped. And so we could plot a whole bunch of these solutions, and indeed we're going to. So again, this is exponential growth or exponential decay, and this is that vertical translation, that shift. So let's do that right now. Okay, so we have this graph of wow, we can do it more like this. We're not really going to deal with negatives. So let's say we have this graph over time, and there's some, long-term behavior of, whatever concentration, or I think we did amount of sugar. We didn't actually do concentration, but this is that amount of sugar that we're approaching, which I think was 2,000 over 3. It's extremely important in this class to label your axes, because your axes are going to mean different things at different times. But right now, speaking of time, let's talk about time being the horizontal component and the amount of sugar as a vertical component. We said there could be a lot of solutions, right? I said we could start with no sugar and we'll approach, that equilibrium amount of sugar. We could also start with a lot of sugar, and again, we'll slowly decay. And it's really everything in between. Maybe we start with a medium amount of sugar and it'll grow like that. Maybe we'll start with a little bit more sugar and it'll go like that. Maybe we're going to start with exactly the amount of sugar, and so on, right? There's infinitely many solutions to this ordinary differential equation. There's infinitely many. Okay? And remember, what differential equation was it? It was this differential equation. So let me copy that so we have something to look at. That was ds dt, the rate of change of the sugar in tablespoons over time in minutes. We said that was equal to 20 minus 3 times however much sugar there was at that time, all divided by 100. This is the differential equation. This is a graph of a bunch of solutions. Again, there are infinitely many, right? Like they all look like this, right? I could draw them all. Well, I can't draw them all. That's not how infinity works, but I could draw a lot of them. Now, notice something very interesting. Look at this differential equation. What is this left-hand side? This is the slope, right? Derivative is slope. This is the slope, the change in s divided by the change in t. This is the slope, and this says the slope at any point can be determined by the amount of sugar at that point. And remember, we can visualize that. We can visualize slope, right? Like here's the slope at a certain point. And what this equation saying, right, is that we can find the slope at a bunch of different points. We could calculate all of these red slopes. Remember, the derivative is the slope of the function. The slope of the function is the slope of the tangent line. So this might be a derivative of -1. It goes down 1 over 1. Or maybe this is a derivative of -1/2. It goes down 1 over 2. Right? We have all these slopes. And in fact, calculating all these slopes is pretty easy. right? We can find the slope of all these solutions at a bunch of different points, right? We could find these slopes. How do we find these slopes? Well, we could take the derivative of the solution, but we don't actually even need this solution. It'd be silly to take the derivative of this solution to find the slopes. We have a much easier way of finding slopes. And that's this, right? If I want to find the slope when s is 0, we can just plug in s is equal 0. When s is 0, the slope is 20. When we're way down here, the slope is 20. It's very steep. And so on. So if I were to plot what all of those slopes look like, I might have a field full of slopes. Okay? And that's going to look like something pretty interesting. So again, let's look at another graph. It's going to be pretty much the same graph. And again, let's have this be time. Let's have this be the amount of sugar in tablespoons. We're going to have the same exact horizontal asymptote. What if I just graph all the slopes? According to this equation, we could calculate this, plug in different values of s. We plug in s equals 0. We got 20. As s gets bigger, the slope is getting smaller, right? So we could, plot a bunch of slopes for different values. When s was that equilibrium point, the slope will be 0. And we can see that it actually didn't matter what time was for all these slopes. We could plot a whole bunch more slopes, and the time doesn't affect it. And again, there's infinitely many things that we could plot. We could plot a whole bunch of slopes. But it's very common to just plot it like every integer or something. And if we just fill this all in, that gives us what's called a slope field. So the slope field is really just using our differential equation to graph a whole bunch of slopes, because remember, there are infinitely many solutions to many differential equations. Since this is an autonomous differential equation, right? It's autonomous because there's no independent variable in the differential equation. There's no t's here, right? That means the slope field is not going to depend on t either, right? It only depends on s. The slope only depends on how high we are. It doesn't change as we move from left to right. So this is a slope field for this differential equation, which is very nice for two reasons, probably more than two reasons. One of which, we can generate this slope field very quickly with the differential equation. If you're confused where this slope field came from, don't worry. We talk about how to build slope fields in the next video, so you don't have to know how to build it yet. So we can do that without an analytic solution at all. We don't need to use separation of variables. We don't need to actually find the solutions. We can just find all the slopes pretty easily because this is a simple formula to plug in values of s. And that'll give us our slopes. We just plot the slopes over here. And when we have a bunch of plotted slopes, it's exciting because we basically have an idea, not exactly, but we have an idea of what the solutions look like. This is qualitative analysis. The last section, we talked about analytical solutions. We found the actual functions that solved our differential equations. Here we're going to talk about slope fields. We're going to be talking about, okay, how can we analyze this? Not exactly, but get an idea of the behavior. And you can see that we can kind of plot what we think might be different solutions by kind of following these curves, right? Like if we follow these tangent lines, these little mini tangent lines, we're going to get different solutions to this equation. All right? And in fact, following these tangent lines is going to lead us to a numerical method as well called Euler's method that we get into in the next section. Okay? So this is the basic outline of what slope fields are. We have a website that I linked in Canvas over here. And you can go up here and write a differential equation. You can choose different variables. So a lot of times we use dy dt, but again, as long as you're consistent, it should work out. Let's graph ours. They don't have an s here, so we're just going to say 20 minus 3y over 100, because that's our dependent variable here is y. And when we do this, when we plot this, we get the following slope field. Again, let me see if I remember how to set the, I specifically chose this one, yeah, because we can set the inputs. Let's say we're gonna look for, I don't remember how many minutes we wanted to look for, maybe 20 minutes, and it was like 500 to 800 tablespoons of sugar or something. I forgot to write down the presets that I wanted to include here, but maybe this isn't quite it. Can look for an hour maybe. And then we'll expand a little bit, 300 to 1,000. Oops. And what you can see is a very similar picture. And we have a slope field. You can see all those slopes. Now watch the power of this web page is I can click anywhere I want and say, let's say I'm here. What happens if we follow the slopes if I'm right here? And it'll plot a portion of the solution. Okay. Let's zoom out in the y coordinates a little bit. Let's go 0 to 2,000. Let's say we start with a whole bunch of sugar. How's that going to change over time? Again, let's start with not very much sugar, and you can just plot a whole bunch of solutions. It'll follow these mini tangent lines and give you an idea of what that solution looks like. Let's say we are at that equilibrium point or close to that equilibrium point. You can see how that's going to go. So we can take a slope field. This website will generate a slope field based on your differential equation. And then you can click on it to get some ideas of what different solutions might look like, which is pretty cool. So we'll be using that to visualize some things in this section, and that's just a general overview of slope fields. Again, reading slope fields is challenging. We have a video for that. Constructing slope fields is challenging. We have a video for that. Also, we're not really ever going to do it by hand. So don't worry, this is just an introduction to give you a little taste of what's coming up. I don't have a clever way of ending the video, so we'll end it with, how will Theodore say goodbye to us? All right, he's sleeping. I'm sorry. Hopefully you're not sleeping. We have another video. Bye-bye.